What is Avogadro number? Avogadro number is the number of gas molecules per 1 mole. The symbol of Avogadro number is Na, and Na equal to 6.02 times 10 to the power 25. That means in 1 mole of molecule, there are 6.02 times 10 to the power 23 number of gas molecules. Wow, it is too large. Next, what is molar mass? Molar mass is the mass of 1 mole of gas. The molar mass of hydrogen gas is equal to 2 grams, and the molar mass of oxygen gas is equal to 32 grams. In this part, you will learn several equations. The first one is the general gas law. The general gas law can be written in the form PV over T equal to constant. The three gases law you have learned before can be deduced from the general gas law. When V is constant, we have P over T equal to constant value if V is constant, right? If T is constant, we have PV equal to constant. Also, when P is constant, we will have V over T is constant. Okay? But when P, V, and T change, then we should use PV over T equal to constant. When we have two sets of data, then we should use the equation P1 V1 over T1 equal to P2 V2 over T2 in our calculation. This is the application of general gas law. Another equation you should learn is the equation of state. This equation is given to be equal to PV equal to nRT, or we can say PV over T equal to nR, and this is the constant value of this one. Okay, in this equation of state, P is the gas pressure, V is the volume of gas, T is the absolute temperature. The unit should be in Kelvin temperature. Okay. R is the molar gas constant, which is a constant value equal to 8.31 joule per mole per K. Remember, R, the value is equal to 8.31. Another term is smaller n. Smaller n is the number of moles of the gas. The kinetic theory of gases, 氣體動力理論, is used to explain the behavior of gas by means of the motion of gas molecules. For example, gas pressure is one of the behavior of the gas. Gas pressure can be explained by the motion of the gas molecule in the way that it is due to the collisions between the gas molecules and the container wall. Let's revise the assumptions for an ideal gas 理想氣體. The assumptions for an ideal gases are the gas molecules are moving randomly. Second, the gas molecule have negligible size. Third, the collision between the gas molecules and the container wall are elastic 彈性碰撞. Fourth, intermolecular forces between the molecules are negligible. That means there are no forces between molecules. Fifth, the time duration in a collision is negligible compared with the time interval between each collision. Under what conditions an ideal gas can be considered as an ideal gas? The assumptions for an ideal gas can be whole if the gas is at high temperature and low pressure. These two conditions must both be true so that real gas can be considered as an ideal gas. So you must remember these two conditions. When a gas is considered as an ideal gas, then we have the kinetic theory equation, which is PV equal to NM C squared over 3. Notice that P is the gas pressure, V is the volume, N is the total number of gas molecules, M is the mass of one gas molecule, and this symbol, okay, is the mean square speed of the gas. Now let's compare the equation of state PV equal to nRT with the kinetic theory equation PV equal to nmc square mean over 3. First, we have nRT equal to nmc square mean over 3. nm c square mean over 3 equal to nRT. And we arrange the term, we got n times mc square mean over 2 equal to 3 over 2 nRT. And this expression mc square mean over 2 is equal to the kinetic energy of one gas molecule, or we say this is the average kinetic energy of gas molecule. This expression is very important. And since n is the total number of molecules, therefore we have n times mc square mean over 2 will be equal to the total kinetic energy of the gas. How to find the total kinetic energy of a gas? This expression equal to 3 over 2 nRT. Therefore, total kinetic energy of gas equal to 3 over 2 nRT. You should use this equation to find the total KE of gas. This is important. And the kinetic energy of only one gas molecule will be found by this equation, which becomes 3 over 2 n RT over n, which is equal to 3 over 2 RT over our Avogadro number Na. And the root mean square speed of the gas can be found by this equation, equal to square root of 3 PV over Nm. Also, the root mean square speed can also be found by using the equation by replacing PV equal to nRT. Therefore, root mean square speed of the gas equal to square root of 3 nRT over Nm, or written in the form equal to square root 3 RT over molar mass m pi. M pi is the molar mass of the gas, and T is the absolute temperature. Therefore, root mean square speed is proportional to the square root of T over M pi. Also, you notice that the total kinetic energy of the gas, or the average kinetic energy of the gas molecule, is proportional to the absolute temperature T. Now spend some time to read question number 1 and number 2. Question number 1. The root mean square speed of the gas is equal to square root 3 RT over the molar mass m pi, equal to square root 3 times 8.31 times 20 plus 273, the absolute temperature, over 0.002 kilogram, the molar mass, which is equal to 1911 meter per second. Since root mean square speed is proportional to square root of absolute temperature over molar mass. For question number 2, the gas hydrogen and oxygen have the same temperature. Therefore, the root mean square speed is proportional to 1 square root of 1 over molar mass. Therefore, the root mean square speed of hydrogen gas to that of oxygen gas is equal to the ratio of the square root of molar mass of oxygen to that of hydrogen, which is equal to the square root of 32 over 2, which is equal to 4. Now spend some time to study question number 3 to number 5. Question number 3. By using the equation PV equal to nRT and substitute the values into this equation, we got the pressure of the gas becomes 3.59 times 10 to the power 5 Pascal. Question number 4. The number of helium molecule N equal to number of mole times Avogadro number equal to 1.2 times 10 to the power 24. Average kinetic energy equal to 3RT over 2Na, which is equal to 6.21 times 10 to the power negative 21 joules. Total KE equal to 3nRT over 2, which is equal to 7480 joules. Question number 5. We apply the general gas law by substituting the values into the equation. We have the new volume of air becomes 54.2 cm cubed